Up to this point, we discussed three types of stresses. We spoke about compressive stress, tensile stress, and we also looked at shear stress. Now we're going to examine what happens to objects, to solid objects undergoing stress when that stress is very large. So if the stress that an object experiences is large enough, that object can fracture or break into two or more pieces. For example, if we have the following column, solid column, that is hanging off of the ceiling, and we apply a tensile force which creates a tensile stress within that object, and the stress is high enough, that object will break, will fracture into two or more pieces, in this case into two pieces. Likewise, if we have another object and we apply a shear stress onto that object and the shear stress is high enough, well, our object will fracture into two or more pieces, in this case once again into two pieces. Now let's talk about the ultimate strength of our object. The ultimate strength of the object is simply the maximum stress value that an object can withstand before it actually fractures. So in this case, if the tensile strength of the object exceeds its ultimate strength, that object will fracture, and the same exact goes for this object. So let's compare and contrast steel objects and marble objects. And let's look specifically at compressive stress. So this compressive stress for steel is 500 times 10 to the 6 newtons per meter squared. In other words, if we have a steel column and the steel column experiences a stress value, a compressive stress value that exceeds this quantity, that steel column will break. And the same exact is true for a marble column. And notice that a steel column is able to withstand a higher compressive stress value than a marble column can. So let's look at the following example. Let's suppose a 2-meter long steel wire with a radius of 0.1 centimeters is used in a piano. Now if it stretches a distance of 0.6 centimeters, we want to calculate the tension that would fracture our steel wire. So here we have our diagram. We have the steel wire, and we're applying a tensile force on both sides. So that basically means that the object, our steel wire, is under tensile strength. So we have to use this quantity, 500 times 10 to the 6 newtons per meter squared, which just happens to be the same value as the compressive. Now that's not always the case. So we're essentially taking the ultimate strength of our steel wire given by this quantity, and we're equating it. Well, notice that the units of our ultimate strength is newtons per meter squared, and that means this is equal to force divided by area. So force divided by area is equal to this quantity, 500 times 10 to the 6 newtons per meter squared. So now we rearrange our equation and we solve for the force. The force is equal to the cross-sectional area of the wire, which is assumed to be circular. So that's pi r squared, where r is simply our radius in meters, which is 0.15 divided by 100. So we have pi multiplied by 0.0015 meters squared, and multiply that quantity by our ultimate strength of our tensile stress. So 500 times 10 to the 6 newtons per meter squared, and we get an approximate tensile force, an approximate tension of 3,500 newtons. In other words, if our object, if this steel wire experiences a tensile force that is equal to or greater than this quantity, or actually greater than this quantity, then that object, our wire, will fracture. It will break into two or more pieces. Let's assume in this case it breaks into two pieces. So once again, any object, any solid object, has the potential to break. Now, when that object breaks really depends on the quantity of force that is applied to that object and the composition of that object. Certain objects are stronger, can withstand higher stress values than other objects, as we saw for steel and marble objects.